Hi, I'm Dr. Christopher Sutton, and welcome back to my Introduction to GIS video series. In this video, we wrap up our Introduction to Coordinate Reference Systems with an examination of datums. A datum allows us to accurately measure locations on Earth's surface. Because different datums can place the same point at different locations, it is important to understand what datums are and why they matter in GIS. A datum is a reference framework that defines the position and orientation of a reference ellipsoid relative to Earth's surface. It provides a coordinate system for mapping and navigation. A datum includes a reference ellipsoid, which is a geometric model of Earth's shape. A datum has an origin, which is a specific point on or within Earth where the ellipsoid is positioned. A datum also has orientation, which is the alignment of the ellipsoid relative to Earth's surface. Because datums use different ellipsoids and reference points, the same physical location on Earth can have different latitude and longitude values depending on the datum used. In early geodetic datums, surveyors used traditional methods such as triangulation and ground surveys to measure positions over limited regions. In these datums, the reference ellipsoid was centered on a specific point on Earth's surface. Often, a well-surveyed control point was chosen as the origin. This approach minimized errors within the region of interest, but did not necessarily represent the Earth as a whole. Modern geodetic datums align the reference ellipsoid to the center of Earth's mass rather than a point on the surface of the planet. This approach aligns the ellipsoid with the geoid, providing a consistent coordinate system that is applicable worldwide. There are two main types of datums: horizontal datums and vertical datums. Horizontal datums are used to locate positions on Earth's surface in terms of latitude and longitude. Think of a horizontal datum as a grid drawn on a reference ellipsoid, which allows you to specify location. The two primary types of horizontal datums are global horizontal datums and local horizontal datums. Global horizontal datums use Earth's center of mass as the origin. They are designed to provide consistent accuracy across the entire globe. There are several global horizontal datums. We will take a closer look at two of these. The first is WGS 84, which is maintained by the National Geospatial-Intelligence Agency, or NGA. This is the standard used by GPS. As I stated in the previous video, there is a WGS 84 ellipsoid and a WGS 84 datum. The WGS 84 ellipsoid is the smooth model of Earth's shape, and the WGS 84 datum is the reference system used to define positions on Earth's surface. There is also the ITRF, which is the International Terrestrial Reference Frame. This is a global reference system maintained by the International Earth Rotation and Reference System Service, or IERS. ITRF provides highly accurate Earth-centered coordinates that account for factors like tectonic motion and crustal deformation. It provides a standardized reference for precise GPS positions. It has been updated several times. The most recent version, ITRF 2020, was released in 2022. Let's look at some of the key features of ITRF 2020. It provides extremely accurate coordinates with millimeter precision for many locations. ITRF 2020 includes velocity models that account for the movement of tectonic plates and other changes over time. It also provides a unified reference frame for the entire planet, making it ideal for global applications like climate monitoring, disaster management, and satellite navigation. It's worth noting that WGS 84 is closely aligned with ITRF. The other major type of horizontal datum is a local horizontal datum. Let's look at some examples of these. The first is NAD 27, which is the North American datum of 1927. NAD 27 is based on the Clark 1866 ellipsoid and was created using ground surveys and measurements. In this datum, the Clark ellipsoid is aligned to a fixed control point on Earth's surface. That control point is located at Meads Ranch, which is in Kansas. NAD 27 was used primarily in North America for geodetic surveys. While it's not used anymore, you might find a lot of data using NAD 27, including historical maps and legacy data like local government records, tax maps, or parcel data. NAD 27 was replaced by the North American datum of 1983, or NAD 83. It is based on the GRS 80 ellipsoid. It provides more uniform accuracy across large areas, and its origin is the center of Earth's mass rather than a position on Earth's surface. It is the standard for most modern GIS applications in North America. When we have different datums, the location of a feature can have different coordinates based on what datum you use. This certainly is the case with NAD 27 and NAD 83. We'll use Seattle's Space Needle as an example of the difference in coordinate position for this object. In NAD 27, the coordinate position for Space Needle was 47 degrees, 37 minutes, 13.76 seconds north, and 122 degrees, 20 minutes, and 57.47 seconds west. In NAD 83, Space Needle's coordinate position is 47 degrees, 37 minutes, and 13.11 seconds north, and 122 degrees, 21 minutes, and 1.93 seconds west. If we plot those two coordinate positions on a map, we would find that they are more than 312 feet apart from each other. The difference in position between these two datums can be very important when dealing with boundaries, parcels, and other data that require precise coordinate positions. We also have local horizontal datums that are regional terrestrial reference frames, meaning that they are based on the International Terrestrial Reference Frame. We have NAD 83 2011, which was an update to the North American datum of 1983 to align with the 2008 version of the ITRF. We have a new North American Terrestrial Reference Frame of 2022, or NATRF 2022, which will replace NAD 83. And it is aligned with the ITRF 2022 version. There are many other regional terrestrial reference frames that align to the ITRF. In addition to horizontal datums, we also have vertical datums. Vertical datums define elevations or depths relative to a reference surface. The zero value in a vertical datum for Earth is called mean sea level. Early vertical datums define mean sea level through tidal gauges. Modern vertical datums are based on the geoid. There are three vertical datums that are worth noting for North America. The first is NGVD 29, which is the National Geodetic Vertical Datum of 1929. It was based on tidal gauge measurements and was used for elevations until the 1980s. It was replaced by NAVD 88, or the North American Vertical Datum of 1988. NAVD 88 measures elevations relative to the geoid. The third vertical datum is the NAPGD 2022, which stands for the North American Pacific Geopotential Datum of 2022 and will replace NAVD 88. It also is based on the geoid. I mentioned that vertical datums are used to calculate elevation. Let's quickly look at how this works. The geoid is used to define mean sea level. GPS measures heights relative to a reference ellipsoid, not the geoid. These elevations are called ellipsoid heights. The difference between an ellipsoidal height and the geoid is called geoid undulation. By combining ellipsoid heights with geoid undulations, NAPGD 2022 calculates orthometric heights, which represent elevations above mean sea level. So the example I gave in the previous video of a mountain having a summit at 1,000 meters above sea level That is an orthometric height. A datum is the foundation of accurate mapping and positioning in GIS. Whether using a local datum or a global datum, the choice impacts how locations align on Earth. If you combine datasets that use different datums, you'll need to transform the coordinates to a common datum to ensure everything aligns correctly in your GIS project.